Welcome to this exciting afternoon session. My name is Anna Grassellino. I'm a senior scientist at Fermilab. I serve as the director of one of the 5 National Quantum Information Science Research Center, SQMS. It is my pleasure and honor this afternoon to moderate this session. And we start with a keynote by a very well-known speaker, Vanessa Chen. Vanessa is the Chief Commercialization Officer and Director of the Office of Technology Transition at the Department of Energy. I had the pleasure to meet her a few weeks back when she visited Fermilab. Dr. Vanessa Chen is the Chief Commercialization Officer, Director of Office Technology Transition at DOE, and she's responsible for advocating and advancing pathways for the commercialization of innovative technologies developed at the DOE national labs, sites, and facilities. Dr. Chen is an innovator who has worked across a wide range of ecosystems, from academia to Fortune 1000 companies to startups. She comes to the DOE on a leave of absence from her position as undergraduate chair of the Material Science and Engineering Department at the University of Pennsylvania School of Engineering and Applied Sciences. So let's welcome Vanessa, and we look forward to her keynote. Thank you.
Thank you, Anna, for the warm introduction. And I'm sorry I'm here in 2 dimensions versus 3 dimensions, but I think that's where the world's going with quantum, so that's okay, right? But I wanted to thank all of you at the Chicago Quantum Exchange for asking me to join you to deliver a keynote. And as Anna mentioned, as the Chief Commercialization Officer and the Director of the Office of Technology Transitions, we have what I think is the most fun job here at DOE, is to think about how do we take the world's top science R&D enterprise and bring to market all the incredible technology research that is being done across our 17 national labs. And I really appreciate the opportunity to address all of you and be in this conversation around quantum information science, what my role is within DOE and what the department's broader efforts are on this. So here at OTT, we work with our 17 national labs. Fermi and Argonne are 2 of them, and also with external stakeholders to really foster partnerships, programs, and policies that encourage technologies to successfully complete the journey from lab bench and into the marketplace. And in particular, what I'm really focused on are what are the gaps or barriers that really make the journey from idea to product most difficult. And we know that this is a topic of great significance in quantum technology. So my vision for OTT is really born out of my own personal story. As Anna mentioned, I come from a science background. I got my PhD from MIT in material science and engineering, which, as everyone knows, is a critical major for quantum. And I was personally frustrated, though, by the impact or lack of impact that my PhD had in the world. I had a first author science paper and all that jazz, but in the end, when I take a look at it, it's really hard for me to articulate how did that help move the needle, right, around where I can improve the world. And this is a fundamental challenge that I think we face in academia as a whole. We teach our students to be very deep technically, which, by the way, is really critical. Don't get me wrong. I really think it's important that we get that deep technical knowledge. But imagine we gave them that deep technical knowledge and also paired it with their ability to see how to have an impact in the world. And that we think beyond just publishing research, which I think is critical. So don't get me wrong, I'm not saying don't publish, but what I want to do is think about the research that we publish. What do we do with those findings, right? And how do those findings lead to impact in the real world? And I think the challenge is that by design, PhDs are more technology push mindset. Since everyone in your lab is focused on researching the same technology, my PhD group was all about block copolymers. And nowhere are we really asking how will our work have an impact on the world? And it would be great if we were made to write a chapter on how our research might be used in the real world. That would be enormously helpful to our graduates to be thinking about how to go from a technology push mindset to more of a market pull mindset. In other words, how do we keep the ideas that we develop and get them out into the real world, rather than examining what innovations the market is demanding and working to fill those gaps with innovation. So one idea is, if we can get our researchers to walk a mile in a practitioner's shoes, then they can see firsthand the problems that the users have and what they might want to be tackling when it comes to their research. And this would include labs, universities, and private industry. And it would be an eye-opening opportunity for participants and will also enable more knowledge sharing as we provide an appreciation for how things work in these other environments. So by reframing how we look at our roles as innovators through curiosity and creativity, which are, by the way, natural skills we develop as scientists, we can really find new ways to enable commercial impact. So when I first got started as the Chief Commercialization Officer in January, one problem that I immediately encountered was the total lack of a common language around technology commercialization. We've spent a lot of time and money supporting different technologies at different stages, but there really isn't a very clear pathway from research to market. There's a lot of different places where the ball can get dropped, and we could potentially leave many promising entrepreneurs or technology out in the cold. And so what I first want to do is make sure everyone was aware what actually is commercialization, and then what are the actual barriers that are preventing us from getting there. So broadly speaking, when you think about commercialization, it's following a four-step track. First is on research, second is on development, third is on demonstration, and fourth is deployment. And what we need to do is help our technologies go from the lab, move through the RD&D continuum so we can get to the marketplace. In research, we really are focused on conducting experiments to show a technology's potential against a certain value proposition. In development, we're designing and building proofs of concepts and validating at the lab scale whether or not those could work. In demonstration, which oftentimes is the hardest phase, is we're potentially building a pilot scale system, and we're starting to test technologies in real world environments. And finally, when we move to deployment, this is when a technology has been de-risked. The economics make sense, and that's really, really important, because if the economics don't make sense and there's no viable business model for a supply chain, then the supply chain won't establish itself. When we get to deployment, you're able to show the economics are there and the technology works. Now, at each of these different steps, technology faces real substantial barriers to moving forward. And they might be technical, they might be engineering related, and of course, financial. And at these critical junctions, you need to be able to figure out how to navigate this. Now, I will tell you that energy technology is a really tough game. It takes a lot of time, a lot of capital, a heroic amount of patience, and quantum is the same way. And so DOE and OTT is coming to solve these problems in really creative and, quite frankly, I think awe-inspiring ways, because we recognize that the implications of quantum information science on our economy and nation could really be transformational. And we really should be the leaders here in the US. We're already starting to see significant commercial interest arising from the promise of quantum technology to provide perfectly secure communications, novel solutions to highly complex optimization problems in finance and healthcare, more accurate measurements of physical phenomena, and far more realistic simulations of the real world, which is really important as you think about climate change and things like that. And we know that this work is already being done across the regions. As Anna mentioned, we have 5 quantum centers that are being led by DOE, and 2 of them are in the Chicago area, Argonne and Fermi's quantum centers. And as such, the Chicagoland region is really poised to support startups developing quantum technology, in particular by leveraging a strong quantum ecosystem with world-class researchers and a really diverse industry base. And one of the first things I did was to help launch the first quantum startup accelerator here in the Chicago region and in the nation. So whether it's the specific work being done here in Chicago or in any number of regional ecosystem, quantum information science really has an important home within the Department of Energy and throughout our broader innovation R&D enterprise. And in fact, quantum can and is being used to address areas within our mission space. For example, we're exploring the ability to use quantum for high particle physics and nuclear fusion research. And at the same time, there are near quantum technologies such as quantum annealing and NISQ computers that can be used to begin developing quantum algorithms. These algorithms can be tested against our arsenal of classical algorithms to discern whether there is a quantum advantage. And by the way, this research is useful even if we find that there is no quantum advantage. We will have the benefit experience and lessons learned for when the time arrives when a fault-tolerant gate-based quantum computer finally arrives. So this example underlines how we can work towards build the skills we need for the future, for technologies that very well may yet to be undiscovered, and by reducing the learning curve so that we can get to work as soon as those opportunities arise. So DOE is engaged in a across-the-board push for innovation. which includes quantum information technologies right alongside other major technology areas. And there's a growing interest in quantum information and its many possible applications. And it's really important to think about quantum information technologies as an enabling technology that has applications in mind as we're developing it. So DOE's Office of Science is one of the lead government supporters of quantum information science. And we're supporting innovation in the space in three main ways. First, by supporting fundamental science that underpins quantum computing, simulation, communication, and sensing. Secondly, by creating tools, equipment, and instrumentation that go beyond what was previously imaginable. And finally, by establishing DOE community resources that enable the entire QIS ecosystem to innovate. So science is really leading the charge on basic science research. And here at OTT, the role we play is to help create a bridge to the program offices and industry to facilitate the rest by exploring use cases that we can find useful and could benefit from quantum. And these use cases are really, really critical if we're going to get to commercialization. Creating those connections is a really important support for quantum technologies. Combinatorial optimization problems may be the low-hanging fruit among these use cases. We also are helping to build partnership inside and outside DOE that's necessary to explore these use cases through these relationships and to extend the innovation ecosystems to quantum information technologies. Additionally, I want to recognize that QEDC has been a great industry partner, and it includes private companies, investors, but also labs and universities that share common interests. We also are involved in an interagency working group on quantum that's led by the National Quantum Coordination Office in the White House's Office of Science and Technology Policy. And we talk regularly with NSF as well, and we, as well as the National Institute of Standards and Technology, NIST, DARPA, and the Department of Defense, and the National Institutes of Health, and more. So at OTT, we really are dot connectors and networkers because we know that high connectivity enables innovation. And through these collaborations, we're trying to understand any market barriers to execution and adoption. We know the business models will also be different for quantum computers, and they will not evolve in the same way as what the Mac or the PC did. We can't rely on an assumption that the computer is a computer is a computer. So by not making assumptions and staying curious, we're expanding the impact of our federal role by leveraging our convening ability to facilitate interactions and demonstrations that help uncover those often nuanced but very high magnitude barriers. And that sets us up to find resolutions and to produce information that empowers our partners to resolve those barriers as well. So I want to share a very specific example with you. We know there are concerns regarding a potential quantum winner and whether there will be enough capital to keep the quantum industry and research alive long enough to achieve building a fault-tolerant gate-based quantum computer. This is a very real and very serious concern, and one that should concern even those who are operating solely at the lab bench. And so we have focused on exploring use cases and trying to find near-term applications of quantum information science, whether it be for computing or for network communication, security, or sensing. So we're coming at it with a very particular focus on the energy sector, looking for places where the use cases will align with DOE applied program offices who can help provide that support. And this is a strategy that has worked in many other types of technologies. If you think about material science and engineering, which is where I come from, oftentimes we may invent new materials where the use case is auto, or aerospace, which is where a lot of the big changes can be made. However, to get there takes a really, really long time. And so if you have a new technology, it's better to go after applications where the barrier to entry is much lower. Oftentimes it's consumer products, where you can go there, try a new technology, build out your supply chain as you look towards the larger applications out there. And so that approach is something we're trying to get to. And the things that we're doing here at OTT to help build bridges, because if we don't build those bridges, then we will get to the quantum winner. And as much as I love Game of Thrones, I really hope winter's not coming here. And we're going to try to help avoid it, because if we can get to some early wins, we can help maintain the momentum that we need for the long haul. So I want to switch gears at this time and speak more directly to the members of the audience here today. And I want to take this opportunity to share with all of you that we're interested at OTT in identifying lab experts that could provide subject matter expertise that supports grid optimization use cases, leveraging near-term quantum algorithms. We really want to gather expertise from the classical arena to help inform those quantum algorithms. Therefore, these lab experts we're looking for need not necessarily be quantum experts themselves. So here's what we're looking for as we have an upcoming workshop with QEDC approaching. Experts in the areas of applied mathematics, for example, combinatorial optimization, near-term quantum computers, so that would be quantum annealing or NISQ, quantum algorithms that can be used on near-term quantum computers, such as quantum annealing, with a particular focus on optimization, and energy grid optimization algorithm developers. If you're any of those folks, I encourage you to reach out to us at OTT, or if you know someone who might be a good fit. And you can read more about OTT and find contact information at energy.gov/technology transitions. Last, I want to thank all of you for the work that you're doing in the quantum space. I want to acknowledge that this is difficult work. It's sci-fi work. It's things that are beyond even our imagination. And the unique challenges of quantum, while exciting, can be absolutely daunting. And we believe that innovation takes an all-hands approach to meet our goals as a nation and for our world. And I want to offer our resources and passion for innovation to you all, and know that we are always looking for ways to help bolster that work. So I'm excited that you have this Chicago Quantum Exchange. It's a great potential for quantum, which is attracting growing interest in an organization like yours. And you're key, right, to fueling the work that needs to be done in this industry. So thank you all once again. I look forward to our further conversation.
Thank you very much, Vanessa. We open now the floor for questions.
So I really like that, the deep dive, that example. And I'd love some other examples of maybe people who are working at national labs. How is it that your office or the labs themselves can help really bring that research that's being developed and make connections with companies, or help the people within the lab license their technology and start their own companies?
So that's a great question. I've had a chance to actually spend time with Anna and her team, and was really blown away by the breadth and depth of the work that's being done in our national labs. And what we're trying to do is think about a strategic portfolio approach so that we can start getting some traction sooner rather than later. I think one of the great things about sitting where I sit, which is at DOE headquarters, is I have a chance to see a lot of different things that a single national lab or even a single company would not be able to see, and finding opportunities for us to make differences in certain applications, which is why we bring up this idea of grid optimization, because I think this is one of the first near-term opportunities for an application. So really what we're trying to do is find where the near-term things are happening, because I think the quantum winter is something we all need to be actively thinking about, bringing those opportunities to different groups like yours right now, and saying, hey, we need some help to think about this. And so really that's where what we're trying to do right now is connect the problems in industry to the technology and the engineers and the scientists who actually can solve it. And that's really the goal of OTT and what we're trying to do. And that's what I've been doing over the past 20 something years, is make that connection. And hopefully we will have success doing it here as well.
Thank you. More questions for Vanessa.
Hey, question from the online audience. In your opinion, what is the greatest barrier to facilitating cooperative technology commercialization that involves academic, industry, and national laboratory scientists?
Great question. I will say there's a couple of barriers. I don't know if I can choose one of them that's the biggest. I think there's a natural tension that industry sometimes have, which is everyone is competing against each other, right, in order to win. And so really trying to align industry to create a cohesive roadmap of things that will allow us to reach the milestones that we need to reach. So if you take a look at Semitech and what was done to enable Moore's Law, if we could do something like that for quantum, I think that would be transformative, but require people to be able to collaborate in ways that may not be natural in industry, because people often want to keep the secret sauce close to home. So I think one natural barrier is, how do you drive open and thoughtful collaboration when industry players individually, right, may be trying to figure out ways that they can get a leg up to others. And that always is a natural tension when you're trying to do something very disruptive and something that is very hard to overcome. I think secondly, another thing that we need to watch out for, which I've seen as I try to connect those different ecosystems together, the private to the public sector to academia, is oftentimes the focus may not be aligned. And so in academia, the focus oftentimes is on publishing papers and really doing some really hard, novel things. In the quantum space, that's true in spades. But then how do we aim it towards things which have more real world applications? And I always see a tension between kind of what industry is looking for and needing and what academia or maybe even some of the national labs may be interested in exploring. And so finding a way to get the right kind of harmony in that partnership is another thing that we will need to be absolutely focused on as well. So those are two things that I've seen in other technologies, and I know that they're here as well.
Thank you. That was a great question, and we look forward to work with your office, Vanessa, to strengthen this. Any more questions from the audience? I think there is one in the back.
Thank you. It was great to hear from you. One question I had on behalf of the new small companies that are coming out of universities, national labs. You mentioned the prospect of a quantum winter, which might very well be real. So for folks who are starting off in this area, what kind of certainties can we expect in the next 5-10 years, say from the government standpoint?
Gosh, I can never predict anything anymore. I think it's something hard where it's challenging to talk about certainties for anybody because nothing is ever certain. What I will say is certain is that we have 5 quantum centers, right, that we are actively investing in from technology and resources standpoint. And when I had a chance to visit Argonne and Fermi's centers, was blown away by the breadth and depth of the kind of work that's being done and the quality of the researchers there. I think what we know for certain is we're going to continue to invest in quantum as a government, because I do think it's a critical technology for the world, not just our nation. And so that will continue. Other than that, I'm not sure what else one can guarantee 5 to 10 years. If I was able to do that, I'm sure it'd be a different profession as well. But I will say quantum is absolutely critical. We need to get there, and we will continue to be focused on trying to help our country with that.
Thank you. So we are almost at the end. If there is any last quick question.
I have another one. Just given your background with undergrads and whatnot, I'd love to hear about your thoughts. How you're involved with students still, even though you're in a different role, and maybe what we as a community really need to do to help them get to the point where that you started out with, where you didn't feel like your work was applicable in the real world.
Great question. I actually have a couple of undergrad alums who are at U Chicago who actually may even be in the audience, so you can reach out to them as well. But right now, I absolutely think that the next generation is critical. Right now, this is apparent, but that's the way the world works and the circle of life. And so we are actively doing things here at DOE to continue to support students. And this is a great plant for something that's actually live right now. I launched a university prize called Energy Tech Up. So look up Energy Tech Up, Office of Technology Transitions, and there's $250,000 prize money for you to go and take a look at DOE National Lab technology and create business plans for them. And if you get chosen, then we're awarding up to $250,000 of money. And the reason why I designed this is I have to tell you, I don't think DOE is great at advertising. And the next generation does not know how much amazing stuff is being done in the Department of Energy. So it's a way for them to start looking at our technology portfolio to see the incredible stuff that is there, and then start thinking, ooh, if I had this, what could I launch in terms of a business? And so it's giving students an opportunity to win money in the context of seeing the amazing stuff we have in our DOE closets and think about ways that it can have an impact in the world. And in terms of, tactical things for those of you who are undergraduate educators that are in the audience, there are some very deliberate things that I did when I was teaching undergrads, especially through the senior design projects that was one of the classes I taught. And I really forced my students to go out and talk to people. They had a cold call people who might be interested in the senior design project they were working on, understanding what the problems are that these people they're cold calling and trying to solve, and why is it that their technology would be able to solve issues that aren't being solved today. And so I actually had them benchmark their technology in terms of dimensions of things that actually matter to the end user, understand what's the incumbent solution and why is it the technology that they're working on could be better than what is being used today. And so I think the more you do to ask undergrads to interact with the real world with the work they're doing, the better poised you'll be to get them to be thinking about things differently. And I'll be honest, one of the reasons why I went back to academia was I realized that the source of a lot of where the change can happen is in the undergraduate curriculum. Because if I had known what I knew after my first few years at McKinsey, working with companies trying to do technology commercialization, I would have approached my PhD completely differently. I would have spent a little bit more time understanding what the real world implications are. And I think I would have been much more impactful. And so that's one of the reasons why I'm so passionate about undergraduate education is it's a perfect time during that 4-year time period to start exploring the real world. So great question. And thank you for the plug to my current Energy Tech Up prize that's live right now.
Thank you very much. Thanks, Vanessa. We are out of time now, but we thank Vanessa again for her perspective, and we look forward to work with your office to tackle the many challenges ahead. Thank you.
Thank you, Anna. Great seeing you.